Swayam Prabha. Digital India. Educated India.
So welcome back. So today I'm going to continue with the discussion following Professor Ratna discussing these contact models, and then continue with the DM. But today I'm going to really present a topic on this multi-scale modeling of a granular media. So I will use the sand as a typical example of a granular media, and to show that how we can really model sand and related sand from a particle scale to a continuum, not only continuum to an engineering scale here, right? And so focus still is what I mentioned on Monday, that how we can really to model the multi-scale and multi-physics nature of granular media here. And so I showed these slides that are, for a typical sand, we have a particle scale size like 1 millimeter to sub-millimeter size, and then collectively, and then it can really to support a engineering building like several hundred meters high, and so that all is really related to a kilometers scales landslides. And how that can relate to, we can correlate them together and to address this multi-scale nature here. And then another nature would be multi-physics, and then granular media is quite often porous media, and then in the pores it can fill with partially or saturated with water, and then these different phases of fluid and can interact with the sand particles in a quite complicated way, and have a lot of significant engineering impact here. And so the focus of my talk today will be focused on these two aspects here. And so first, how we can really do a multi-scale modeling of sand here, right? And so I first wish to present this multi-scale problem here. Okay, and I mentioned before that we have a typical engineering problem like this engineering slope and the landslide. That scale typically have a scale like several hundred meters and to even over 1 kilometers. And then another skill that we typically deal with would be engineering as a laboratory skill that we take a soil sample, send sample to the lab and prepare soil samples and then do a lot of tests and obtain data. And this data and this kind of sample we call representative volume element here. And then back down and to the particle scale, and then there'll be a grain scale thing. And then the length scale, as we can tell, that is ranged from kilometers or 1,000 meters, that scale, and down to this meso scale typically is less than 1 meter, and to several like 30, 40, even 50 centimeters, that size. And then to the macro scale, we call it at the grain scale, that is a sub-millimeter scale here, right? So this multi-scale problem is quite challenging. You can tell that the length scale have a range of 7 or 8 order of magnitude here, right? Okay, and so typically we give a term engineering scale we call the macro here, and then the RVE scale we call it meso, and this grain scale we call it macro here. And then traditionally, how we can deal with this multi-scale problem? The thing that traditionally is that we deal with this engineering scale problems and using so-called continuum mechanics. For example, we propose a model, consider model, and they we calibrate the model by this mesoscale RVE laboratory test, and then implement the model into numerical code like FEM, IMPM, OSP, then solve the engineering problem here. And then the Professor Ratna discussed probably yesterday, and the DEM basically offer a typical micromechanics approach for us really to study the particle scale physics of the granular and then collectively to evaluate their homogeneous response. And typically we can really use DM. Also, sometimes people use MD or physics engine for that purpose. So these are the different methods people deal with it here, right? And then for the continuum approach, so these are the typical way people follow for the engineering problem first, that we define the problem, whether it's a quasi-static, dynamic, whether small or large deformation is a concern, or whether we need to deal with string localization and the discontinuous deformation, or we need to consider substructure interaction, cracking, multi-phase problem. So these are the engineering problem nature that we need to define our problem here. And then we choose the proper numerical tools, and including FEM, SPFEM, is basically smooth particle FEM. It's basically a variation of FEM, or XFEM is still suitable for this fracture or discontinuous deformation simulations, or MPM, SPH, EFM, and others here. And once we do that, a key point is that in this continuum approach, at the certain like FEM at the Gaussian integration point, we need to assume a we need to assume a constitutive model to represent this the constitutive response of this continuum medium, and it is basically typically based on continuum medium theory. And then we consider either rate independent or the dependent constitutive model and other features. And then we put this constitutive model at this Gaussian integration point. And then, of course, the model parameter need to be calibrated, and then we solve the problem, get numerical results. This is what we do here. So from engineering problem to choose a numerical method, and then to assume a constitutive model for each Gaussian integration point, and then to get a numerical solution. So these are the typical continuum mechanics approach that we follow here. And then the approach has been quite popular, or we call it, they are prevailing approach for more than 60, 70 years already. Okay, but it is not without drawbacks here. Okay, so essentially, so what we do is we need to assume a constitutive model, and this constitutive model has been historically developed over quite a lot of different model types here. Okay, and for example, back in 1678, the famous Hooke's law, and the model parameter plotted here, vertical axis with indicator the number of model parameter involved, and then horizontal indicator the constitutive model, continuum-based model, and their timeline here. So the Hooke's law is typically pure elastic, linear elastic model. It contains two model parameters. And then further, if we consider failure, and then we incorporate more coolant failure criterion into it, and then we get a four parameter model parameter needed here. And then back in 1960s and 70s, then this modified chemical model and original chemical model, they need 6 model parameter here. And then the famous hyperbolic model proposed by Duncan and John involved 10 model parameters. And while the famous hardening soil model in praxis need 11 model parameters. And then if we further need to really consider the anisotropy, like inherent anisotropy, where this model does not consider fabric evolution, is a fixed anisotropy, we need 15 model parameter. But if you further want to really consider evolving fabric, and also consider that the evolving fabric converts to an anisotropic critical state, and then you need a 17 model parameter, and this is for the triaxial condition. And then if you want to consider a general stress condition, you need at least 18 model parameters. That for monotonic loading. But if you want to consider cyclic loading for this model, and you need further 22 model parameters. As you can see, this trend. If you want to realistically or more accurately characterize the cell response or send response, and then for all kind of loading conditions, and the increase in model parameter is as we can see here, is linear increase here, right? And so with so many model parameters involved, and then the model most likely we call it phenomenological model. So what does this mean, phenomenological here? It means that some model parameter has a clear physical significance so that we can design a definite laboratory test to determine their value. But many of these model parameters, for example, among these 22 model parameters, there are about 10 also model parameters. We cannot, they don't have clear physical meaning, so that we cannot design a certain laboratory test to determine their value directly. So what we can do is basically we test the cell response and get the experimental data, and then try to really fit the model prediction curve with this experimental data. And this curve fitting process is mostly for those model parameters. And because the involvement of those model parameters in such a complex model, and the model is called a phenomenological model here, right? So we actually rely heavily on this phenomenological model in continuum mechanics approach. And meanwhile, that the DM has been proposed since the 1979, and it has been widely used in a lot of applications, including that how we model cell priming, send response. We can model dense, loose, or medium dense that in joint or unjoined condition get to understand the critical state cell mechanics. But to apply the DM directly for an engineering problem, and if you want to faithfully respect the grain size and grain size distribution, and then it's not likely that you can use DM to solve such a problem. You can imagine that for a typical laboratory test samples, and for sand grains, and you need billions of DM particles to simulate it, and that for laboratory test specimen. But if you want to simulate such engineering problems, and now the modern computational tool, and we don't have such capacity to solve such a problem here. Okay, so by far the DM is not realistic for engineer application yet, because of scaling laws, shape, and other physical features here. So it's only it can be best used as a virtual element test. So element testing is basically the laboratory small sample test here, right? Okay, and so the limitation for DM applied to grinder media problem is limited to a small scale and virtual element test on here, right? And so now we have three skills to consider at least. One is the engineering macro skill represent a typical boundary value problem here. And then we have a grain skill, and then at the particle skill, and then there's the laboratory skill here. And how we can really to bridge these three skills together, and then to relate this particle skill physics and mechanisms, and then use that to explain this engineering skill or boundary value problem skill that are phenomena or observation. And then we can use a so-called RV skill that is really the bridge of them here, right? And so this is the key problem that we want to break the separate skill here, right? Okay, and so as I mentioned in the previous slides, the current practice that we separate the two skills. And either we consider only the macro boundary value problem skill and RV only, or we consider the macro mechanics skill or the particle skill and to do only understand the material behavior here. So those are the different applications. The continuum mechanics and typically feature this phenomenological model, and then need laboratory test. And then also you need to propose new models to account for different loading conditions here, right? Okay, so it's the whole process is very costly and loading path dependent and problem specific here. So those are the other limitations here for the continuum approach. And then for the micromechanics, and then we can faithfully consider the mineralogy and the morphology, surface attributes, the contact, friction, rolling, sliding, breakage, those the particle skin physics here, okay? And then we can use other DM or other approach for that, and then for a better understanding how this particle skin physics play a role. But as I mentioned, it's quite computational expensive, and then there's difficulty and in many levels for characterization, and also how to really map this physical image to a digital one, and you always lost some certain resolution here. So it remains to be a virtual element test at the best here. Okay, and so our goal is translate to break this the boundaries separating the different skills here. So we want to have a direct dialogue among the three skills here. And then it's going to be unique for granular meter, because you would see that a multi-skill or homogenization is quite a fancy word for many other engineering science, like material science. They do homogenization, but that is a so-called it's quite different from a granular meter, because for those material science, they want you to design a engineering material and it's with microstructure, for example. And the microstructure typically is periodical, and they don't have such features that are quite unique for granular meter, like loading and history dependent here. And so for granular meter, we don't have such a periodical microstructure that we can assume or we can develop. And then we need to capture the load history, loading history, and a path-dependent feature, and also the multi-physics nature that the pores can be filled with a pore fluid or pore liquid and gas here. Okay, and also we need to have multiple information passing, so-called multiple information passing that is in contrast with the material science. They design microstructure. They only want you to do it bottom up. Want you to estimate the continuum level material property. This is one-way information passing up. But for the granular meter, we want to have multiple information, because we want to see the particle skill physics, how that play a role on the continuum response. But also we want to see that at the continuum level, what are the loading conditions, the boundary condition at a certain condition will affect the material response. Okay, and then that's the way that we call it multi-way information passing here, right? And then so this is the way that we do it numerically, and we want to develop a computational framework. We call it computational multi-skill modeling scheme here. And then for the boundary value problem at an engineering scale, that we still use a continuum numerical approach, like a finite element method or material point method here, right? And then at the RV and particle scale that we use DM typically, and then we couple this DM with FEM or MPM together in a hierarchical coupling way. And this is what we call the continuum discrete coupling here, right? Okay, and in that coupling, and then we can really to make a full advantage of both skills approach, like FEM and a DM, okay, and then to tackle this multi-skill problem there. And so this is the way that we use a typical finite element method and a typical DM and doing a coupling. Here term means a coupling. Here the coupling means that it's gonna be a hierarchical coupling. What is hierarchical? In this way, just demonstration, FEM can solve a lot of boundary value problems as I showed here. And later on also show some features, okay? And the DM can really to use the particle contact levels, grain-scale physics, and then to also we can replicate the different shapes, and then also shape can be more realistic mapping from this actually city, and or consider other particle scales physics, and then so here's the way that how we do the coupling. And then we call it hierarchical mean that the hierarchy of this length scale here, right? And the engineering boundary value problem scale that we still use FEM to discretize the whole domain by different FEM mesh here. So at each material point of this or integration point of this FEM mesh, and then we put a discrete element assembly as a representative volume element here. And this RV is going to be receive the corresponding deformation and other state variables as the boundary condition. And then this boundary condition is going to be prescribed on this RVE. And then we load this RVE at its boundary conditions and get a deformed RVE. And this deformed from this deformed RVE, and then we can extract or we call homogenize required quantity like a stress or update stress and the tangent operators, which are required by this FEM. And then we can use this quantity extract from RVE, from DM solutions to feed this FEM solver and to further advance the computation of the FEM computation here. Right? So this will form a loop because that during the calculation we need a certain iterative numerical iterations to reach certain equilibrium, right? So, but this is the we apply the load in the incremental way. But the whole idea in this way, this way, the advantage is that help us to bypass the continuum phenomenological assumption, and also we can really consider to certain degrees this macro scale detailed particle shape, friction, and other features as the way we wish. It's going to be a top-down, bottom-up. Top-down means from this engineering scale, RVE levels, down to this FEM level, this engineering scales to this RVE scale, and further to this RVE scale to the particle scale. Yeah, right? And also it's bottom up, meaning that we homogenize the particle scale in action, and from this RVE, and then to get this engineering scales material response that is needed for this FEM computation here. And so in this loop, and then we can establish a direct link between this macro observation with this micro physics here. Okay. And then because of the whole process, we still respect the particle scale physics of the granular, and so we can handle a loading path and state-dependent behaviors in a quite a natural way. And the whole process, we need the computation will memorize the previous deformed configuration of RVE, and then this will make the so-called loading path dependency naturally can be followed here. So this is the concept of this hierarchical multi-scale modeling, or hierarchical continuum discrete coupling here, right? In this way, as you can tell, there we can really solve an engineering scale problem, but meanwhile data response is derived directly from this particle scale physics by DEM here. I give you one example. first, how we can really establish a micro bridging. I use one typical phenomenon that we have observed quite often, string localization. Okay, and to show that how we can relate to particle skew physics like rotation, and then anisotropy, feedback evolution, even power fluid flow, and then to relate to their observation of the shear band here. And I use this as one example here. Here we consider a laboratory test of a biaxial shear test. So this is the back specimen, and we discretized by FEM mesh, like we use rectangular mesh here. Okay, and then on the two sides we apply this confining pressure, and then the bottom center is fixed, and the top we apply a loading platen. Loading platen can be smooth, or we can really make this rough. Means that smooth means that it can really spread laterally, and rough means that we need to restrain their lateral spreading here. Okay, and then instead of assuming a constant model, now at each Gaussian integration point of this mesh, and we unband a RVE. This RVE is generated by non-spherical particle. Now we use this peanut shape particles to generate assembly. This assembly can be generated in different preferred orientation of bedding plan. And then if the bedding plan, this is the bedding plan with in a horizontal direction, and this is in 45 degrees, and this is in the 70 degree, and this is random, means that more or less is isotropic. So we want to consider the initial isotropy of these samples. How does that affect response here? On the right is this bit of simulation of these multi-scale simulations on the smooth boundary conditions and the rough boundary conditions in two cases here. As you can tell, there are now in a smooth case that one single shear band occurs on the rough band, and at the beginning also you have a single shear band is quite similar to the smooth one, but later on in the rough boundary conditions, and you have a secondary shear band, and eventually form a cross-shaped shear band, which is different than smooth case here, right? And so in a sense that even for the smooth case, that different bending plane angles, like 22.5 degrees bending plane, we have a shear band along these directions. Well, if we consider a 45-degree bending plane, and then the shear band will form along this direction. Okay, and then for the rough boundaries, and this is how the first primary and the secondary shear band occurs here. And essentially, this is have a close correlation with the shear force, shear stress developed along the top surface and by this rough platen. Okay, and essentially at the beginning, you have a relatively symmetric shear force developed from when the sample is pushed down, and then with the development of this the dominant or primary shear band, and then the reaction shear force applied to the sample will dominantly from left to right. Okay, and this will be further reduced, and then it changes slightly directions, and then when it is changes certain direction, magnitude and second shear band will occur, and there's no shear force, reaction force to the smooth band, so there's only one dominator pattern here. So this is basically explain the boundary condition will affect the formation of shear band here. Okay, we could also establish some such correlation here. And typically for shear band in the granular mechanics study, and we use shear string or divitropic string to represent it. Okay, And with this multi-scale modeling, we can really derive more parameters and do it homogeneous. One would be this called a particle orientation-based fabric. I mentioned it on Monday, and it defined by this peanut-shaped preferred orientation, and we sum up the orientation together, and then we get this fabric tensor. It's called a particle orientation-based fabric, and then we can get this first secondary invariance FP, and then to denote it, and we find this fabric FP and correlated with the shear strength very well, and it can be used as equivalent variables for localization or indicator. And another variable is the average particle rotation. And in the single shear band case, and also we can really do homogenize the one the RVE, their average rotations over the whole process, and then to get accumulated one, and that indicated quite nicely the shear band are the same as the shear strain here, right? So regarding this is the left is the smooth boundary condition case. Right is the raw boundary condition case. It's quite interesting. You can tell here. And then in the raw boundary condition case, and then at the center part of the samples, the rotation will cancel out. At the beginning, probably you could have a dominant rotation just like this one at these positions. But when the secondary shear band developed, and this part of this RVE, their rotation can rotate back. Like if originally it's clockwise, and then later on it's anti-clockwise, and then eventually have a less rotation at the center and during the shear band localization. So those are the different localization indicator that we can derive based on these RVE levels. And also, I want you to see that how this multi-scale approach of a so-called macro bridging here. We look at this smooth case. One of the smooth case, we develop a shear band like this one, this pattern here, and then we are wondering that what is the difference of the material point within the shear band like B, and in comparison with the material point outside the shear band like A here. Okay, and then we further look at the point A here, their response. We track their stress strain relations. These are the typical stress strain relations, right? Is loading and unloading here. Okay, their dilation curve is also doing this way, loading and unloading here, right? And the stress path or loading path is doing this way, loading and unloading here. And also we monitoring this fabric anisotropy, and one we use the particle orientation based, the other the contact normal based, and we find the particle orientation based and nearly has no change at all, but the contact normal based will do evolution like this one and get it back here. Also, we look at the so-called the microstructure. Here, the dashed line square indicated the original RVE size at the beginning of the loading, and then this the contact network indicated by this bar-like, and as you can see the particle inside him, and these are the strong force chain and weak force chain as I mentioned before, and then this indicator at the end of the shear band for point A, this is the contact network here. And so we can tell that from the material point A, from this RV response, and we can see that it normally follow a drain loading to unloading, and the volumetric change is relatively small. And then indeed it change to a little bit of contraction here, and then the contact force network have a small change here, and FP is then changed and FC changed a lot here. And then we look at point B, and then we also extract all these quantities. And then the stress strain relations is like this black curve here, is going quickly to a peak and then do its softening and then the fluctuation until it reaches to relatively steady. His dilation curve is instant contraction and then go dilation into a steady state. This is a stress path going this way and then going this way here. And this is a fabric evolution and contact normal and orientation based, particle orientation based, both will evolve significantly and both evolve slightly to a quickly to a peak. And also here FP is milder, and then they both evolve significantly to a steady state. And this steady state in some kind we call a critical state here. Okay. And more importantly, if we look at the initial RVE size, and then this will be the final RVE contact force network. And this different distortion shape indicates severe shear deformation. As you can see by the end, the shear deformation can amount up to 200% here. Okay. So as you can see here, material point B and material point A exhibit quite different material response. For point B, we have a loading and peak and softening. And their volumetric change is from contraction and then to dilation. And here, this is a majority contraction. And then the severe distortion and shown by this contact force network. And the shear deformation is much larger. It's 200%, and here is only 7% here. And also we observed for this fabric and particle-based fabric and contact normal-based fabric, and they both evolve significantly, but they won't evolve in the same pace. We call it unsynchronized evolution. But both will evolve to a steady state. Here we in our paper we quantify it indicate a critical state that is widely known in cell mechanics. So critical state can be formed within the material point within the shear band. So this is what we do. We relate to this particle to material response, and then with this shear band observation. Okay, we can also do other phenomena. For example, we can embed a relatively loose sample, initially loose samples at a Gaussian integration point, and then we substitute such samples to cyclic loading. We apply cyclic loading, and then left and right is periodic boundary, and then we can really use that to investigate the liquefaction. And for loose samples and under the different circular load, you can see here the effective stress will approach to very small values, and also the shear stiffness of shear modulus. Okay, and then you can really see this the damping this shear degradations, the shear stiffness will gradually become very small, so that the whole sample will exhibit liquefaction. Also, we examine the this RV levels, this contact force network, when liquefaction occurs at this point, and then we can see very unconnected and small force network, force chain existed. And so the whole sample essentially has no capacity to sustain external shear. This is how in earthquake engineering liquefaction happens. We can use this one to really to simulate to capture this liquefaction phenomenon. Okay, I want to further to show examples how this method can be used to model the engineering school problems here. One problem in civil engineering is a retaining wall. But if even you are in other engineering field, you can always observe that in daily life, we have to build a lot of retaining walls along the roadside or along the slope like this one. So this retaining wall is very important civil structure. Okay, and we have a retaining wall like this one we simulated, and then it's gonna be a supporter such a soil body and sand body here, and on top we have a certain surcharge here. Again, that we embed different RVE at the machine point here. The wall can be moved in a different way, in a translational way, horizontally. It can also move along, use the bottom of the hinge, and then to rotate on this way or on this way. So when it move away from the soil, we call it active mode. When it's really move toward the soil and push the soil, we call it passive mode. Okay. Of course, we can also use the top of the hinge and to study this movement. And this is the simulation results here. Right? Okay. And so when we have a translation movement, right? And then we could have a passive and active mode. Active is the move away, and passive is a move push the soil here. So it will give us different shear band patterns, and the shear band patterns, this shear band phenomenon has been well studied in some kinds for a long time, like over probably 100 years. And then people have developed some theoretical solutions of the validation here. Okay. And so that is one example. We can use this multi-scale to predict this retaining wall failure and then the failure patterns here. Another problem would be our building foundations here. We can really suppose that we want to build a high-rise building or mid-level building here, and then we need to first build a foundation. Here, the typical foundations, we assume that this one can be modeled by this plate, this half width of plate. We cut off at the center, the symmetric center. There'll be another half here, and this will be a soil body. And we again apply certain surcharge here. This will be a simulation results that when we put a superstructure load onto this foundation weight, we call footing, and then when the footing is pushed increased, and then there will be generated such a shear band here. And this shear band, and at a certain place, this we call a rigid zone. Here is called a rotational zone, and this will be a shear failure zone. And this shear failure and can generate towards through this ground level. Again, that this is a place, this is a well-studied problem in some kinds, and by Tasaki and by other scholars. And they have developed theoretical solutions and to estimate the bearing capacity. So what is the maximum load that we can apply, and then to reach such a general failure mode, and then use that maximum load to estimate the bearing capacity of the soil foundation. And this is our simulation here. This is the further comparison that we can compare our solution with the analytical solution, even for this angle, this rigid zone angle, and also this shear rotational zone angles here. And then we can further compare the key area there, microstructure change. So this is the rigid footing example, the important geotech engineering problems here. We can also relate to study other problems like in the petroleum engineering, and when we do hydraulic fracturing, and we really push the wall of this the surrounding like a sandstone or other oil bearing sediment. Okay, and then these other sample we simulated by two different problems. One is a quarter problem, the other is a full domain here. So when we really push, and then it will naturally form such a interesting shear band pattern here, right? And also when we do this two set of problem setting, and we want to investigate the difference of this quarter domain with the full domain, and we find quarter domain sometimes we could really introduce some kind of artificial boundary condition, like this shear band should really penetrate through this one rather than reflect to this part here. So this is the artificial artifacts by this boundary condition. And also remind us, when we really set up the problem, we need to set up a problem, right? So, but this is another boundary vital problem that we can relate to see. By the way, that this quad domain and this full domain, they can produce roughly the same global stress-strain relationship. Okay. For that, and then we in the previous other sample, even the engineering problem, we assume that the grinder meter is dry, or if it's not dry, it's totally fully drained condition, so that we don't really need to consider the pore pressure influence. But quite often that we need to consider the grinder meter is partially saturated and saturated. It's become so complicated. First, we need really we consider saturated going in the middle case here, right? And ideally, that we need to consider the pore fluid flow within the pores, like this what I showed here. But that one I'm going to address in the later lecture. But here I wanted to show that we can really to further extend this multi-scale approach and to model this saturated grinder sand and through this hydromechanical carving. In a typical continuum mechanics approach, like in FEM, we need to solve these two governing equations. And one is a total stress governing the solid scattering, the whole mixture. And then we need to also consider the pore pressure, and which is related to other pressure gradient and also the velocity as well as the permeability. So here we want to introduce a very famous principle of effective stress introduced by Kartasage in some mechanics. And he proposed that for a saturated granular soil, granular meter, and then with a substitute external load sigma, and this sigma is going to be sustained or shared by two major parts. One part is shared by this interparticle friction, interparticle contact force established among the particles. The other part would be this by the pore fluid yield here. And so the total stress is going to be a summation of this sigma prime, which is the interparticle contact force, and the other part with the pressure. Okay, and so this is the effective stress principle here. And then so we can really use this concept. And if we use a DM simulation, and then we can homogenize the DM simulation by such a we call it ODAS formulation and other formulations to homogenize this one. This one will give us the interparticle contact force. And then we homogenize, and this one is exactly what Tasaki mentioned as the effective stress. Okay, so we can use effective stress concept and derived from DM here. And about this pore pressure, and we used as a variable, we are going to solve as a global or macro variables, and we don't really consider explicitly at the particle scale. In this way, you can save a lot of computational cost, and then, but essentially, we still can really solve this saturated meter problem here. Okay, and so this is what we do. We include this principle of effective stress by Sage, and then consider the DM results will give us the effective stress here. And then we use a famous Gingrich and Chan's UP formulation where we consider global variables, include this nodal displacement for the global mesh, and also the pore pressure that goes in integration pore here. And use that as a two set of the unknown variables, and also for those quantities, we still could prescribe this the deformation, but at a certain pore pressure levels, and we solve this RVE here. And after we solve it, and then we extract the effective stress, and also we update this in the solving. Also, we can also extract this permeability. Permeability is related to the pore size distributions and pore size overall. And then we can use a simplification. We use this famous KC equation to extract the updated permeability and extract the permeability, effective stress, and pore pressure also will change because the pore size changes here. Okay, our volume ratio change, and then we update the pore size, pore pressure, and we extract the tangent pore operator, and then we can solve this FEM and for this saturated hydromechanical coupling problem here. Okay, and so this is how we tackle that here. So we updated this quantity, and we can benchmark to very famous 1D consolidation problem solved by Tasaki compared to his results. It's basically saturated soil column, and we apply a surcharge, let it settle down, and then during the settle down, the pressure will dissipate, and then to zero excess pore pressure. And this is the 1D, and this is 2D, and then in the 2D case, we also have an analytical solution, and then by Gibson, and then we can also capture so-called Mendel-Carrier effect. You have a slight increase of pore pressure, excess pore pressure, and then further pore pressure will drop down to 0. So this is to benchmark. Now we use this concept to look back this the same problem that we treated before. But here, instead of a dry specimen, we consider this specimen is a saturated soil sand. And then during the simulation, we assume that we put a membrane and the surrounding sample. We won't allow the sample to dissipate any water. So this creates a so-called undrained condition. The water cannot be dissipated out of sample, but it can move within the sample here. We still use this multi-scale approach, and on the right, it basically is a simulation results. You can see here, we generate shear bond, and then during the generation, we could have certain instant that you have a arrow, shown that is called a Darcy flux, the water Darcy flux, and flow. Apparently, the arrow direction indicated that the water from the surrounding soils will flow into the shear band here. Okay, and that is because within the shear band, the volume or the volume ratio will be increased, the power will be enlarged, and then generate a lower pressure, generate hydraulic gradient, high outside and low inside, and it will drive the water flow into it. And then so this is the further capture that during the different thing, and you can have a certain initiation of the Darcy flux flow from this side to this shear band, and there'll be a higher flux, and then you generate a shear band like that. So this is a quite an interesting hydromechanical coupling phenomenon we have captured here. And now we have insert a dense RV samples, dense packing, and for it generates shear band. But now if we insert a loose samples and to simulate the same problem, and this is what we got here. And we are going to typically generate liquefaction and collapse. And once the liquefaction occurs, and then there'll be no shear band, but the pore pressure will essentially excess pore pressure will increase, and then the effective stress will decrease. Some sample is no longer strong enough to sustain shear and collapse. So this is a liquefaction phenomenon here. And then further, and we wanted to show the same framework can be extended to other phenomena, like if we want to further consider temperature. And we show here the thermomechanical coupling granular. And essentially, what we do is for the here I showed a figure as MPM. Indeed, we can also use FEM. Okay, and so to consider two layers, one is MPM. To consider FEM, consider this displacement and also this temperature. And then at the particle levels, what we do is we consider both mechanical response, and then using the same contact model that we Professor Ratna mentioned yesterday. And then, but we also consider that each particle will serve their center of the serve each particle will serve the heat reservoir. Okay, and the center is the reservoir center here. Okay, and then their branch vector will serve the heat pipe. The heat conduction will transfer through the contact here. Okay, and then from this mechanism, this thermal expansion model, we can really do once when this heat conduction occurs, and then we'll change their temperature, and then they will generate certain thermal expansion or contraction. And this thermal contraction will further change the contact and also their overlap at the contact. This will change the contact force. Okay. Of course, the force mechanical response will change this contact patterns overlap will also affect this thermal conduction. So this is how we develop a particle scale thermal mechanical coupling. Here we don't consider polarity yet, right? And then we can further do some benchmark. Here is basically is a 1D expansion test, right? And a 1D thermal conduction test. And on the right, basically is coupled. We can maintain constant pressure, but change the temperature boundaries, heat on one side, okay, or doing cyclic loading test, or we load at this one and then to fix the other one. These are the basically thermomechanical coupling example that we can show from here. These are the further examples. Suppose that we have a frozen soil. Basically, it's a soil and with the S and divide amount of soil particles. We heated the soil sample from left-hand side, so temperature change, temperature increase, the S will be melted, and then the bond will lost, and then this will lower down the strength of the frozen soil. It will generate the collapse behaviors here, right? This is a further demonstrate example that we can suppose here is the thermal power, and the increase of power temperature will change the temperature field, and then also affect this S distribution, and then to drive this soil slope collapse. Okay, so this is what we call the thawing induced slope failure. Okay, this is a further demonstration of this one, and the whole process here. And so with that, and then I want to quickly demonstrate another extension that we can extend this multi-scale modeling approach to a cohesive granular meter. And then by cohesive mean that, and where I use one example, it's called high porosity granular rocks here. And the granular rock is quite an important rock formation. And for example, a lot of petroleum oils and natural gas are stored in the high porosity sandstone. And sandstone is basically a high porosity granular rock. And then in this sandstone, typically a phenomenon is called deformation band. You can have a shear band like that, but you can have a compaction band. So called compaction band is basically you have a compaction, you have a band formed perpendicular to the compaction direction. It's called a compaction band. This is quite a phenomenon interesting in a way on its mechanism, on its physics itself, but also economically, the compaction band matters significantly to the petroleum engineering, because according to some study, and once a granular rock, a sandstone form compaction band, their permeability can reduce by several magnitude here, for example. And this is original, and then it can really reduce to second magnitude. Okay, and this will affect this energy industry in a way that when we want to extract the oil or gas from this sandstone, or we want to do this CO2 sequestration, which drops the CO2 unit, sorry, or for the nuclear waste disposal, and for this aquifer management, they all matter, permeability matters. That's why an important phenomenon we wanted to deal with this problem by this multi-skill modeling, and then we consider a granular rock formations as a boundary value problem. We take a sample of RVE and we incorporate the RVE level of physics here. So what we do is the same framework developed from my former student Ningguo and Huanren Wu, as using the same framework as I introduced before here. But on RVE levels, we introduce so-called bound here. And so we want to introduce, generate a high porosity RVE packing. So we have a normal, we generate RVE here, and then with isotropic consolidation, and then we add a cohesive bond between the contact points of the RVEs here, right? And then we randomly removed some kind of big particles, and in this RVE, we generate big part here. Okay, and then we finally packed some samples to a initial stress level here. Here we develop a bounded particle models here. Okay. And also here we consider so-called dual porosity RVE. These are the big pores, and also within the small particles, there are still small pores. This is what we call the dual porosity RVE here. And also we calibrated this RVE microstructure with the X-ray tomography of this twofold demonstrate. This is basically a limestone that is typically found in France, and we collaborated the Grenoble lab, and then to calibrate this model, and this is their X-rays, and then we also calibrated the particle density and other part here. This is we test the sample and compared with the experiments, and they match very well on all the parameters that we indicated here. And here is a simulation, simulated a compaction here. Okay, these are the simulation, and so on the left is the shear strain, on the right is volumetric strain, and so the red one indicated it is a compacted or dense, and then on the, in the middle the gray part is basically loose, because you can imagine a high porosity limestone initially is relatively porous and loose, and then when we compress it and compact it dense from the two ends, and so this is called a frontal propagation of the compaction band here, and then the shear strain and the volumetric strain correlate very well here. This is the whole process that we produce this compaction band compaction front evolution here. This is the further comparison. So on the right is experiment, on the left is our simulation here. Okay, sorry, bottom is simulation. Yeah, bottom simulation on top is basically the experimental results here, and as you can see that their correlation is quite consistent here. Okay, and so this is just serve the validation that we can really reproduce the compression front or compression band formation in granular rock, in high porosity granular rock. And then what is the interesting data, the geologist or geophysicist, and also the working in the petroleum engineering, they are interested in what condition of the full kinematic spectrum of deformation band can be formed. The compression band is what we see here. We compact from top, and then we form a densified band in the middle here. And then with different loading condition, we can really to change from a compression band to a shear band, pure shear band, and in between the compactive shear band or the dilative shear band, and then to a so-called pure dilation band here. Basically, you extend it and form a loosened part and the dilative part in the middle here. Okay, so what we do is we want to reproduce this one again. That we use such a set up and then to insert such a high porosity RBE and with the in at this Gauss integration point. This is what we generated here. And then we apply different boundary conditions, especially confining pressure, and then to really to get, and this is the whole spectrum deformation band that we generated by our RVE, by our multi-scale modeling. And this, if you use pure DM simulation, you can never done that because there are a lot of other factors that you need to control really to do that here. And so this is a typical RVE contact force network we can visualize from the different simulations. Compression band you can see here is purely volumetric compression here. Shear band, you have certain shear deformation developed. This is a compactive shear band. This is a simple shear band. This is dilative shear band. This is a shear enhanced dilation band. Here is a pure dilation band here. And pure dilation band, you can see a big pore formed in the soil here. And then we can also further use our approach. We can define another classification index. We use the volumetric strain versus the shear strain and to define that. And with these factors, and then so this can really help us to identify the temporal changes of this shear band. This is another case. We have a shear band. We have a dilative shear band occurs. Okay, and then if we further decrease the sigma, the confining pressure from 20 to 10, okay, and then what we do is at a high confinement we have a compactive shear band here, but if we have a reduced confining pressure, what do we see here? And only the reduction of this confinement will first give us a compaction band first, and then you will further develop a shear band like this one here. It still remains to be compactive shear band here, right? So this is a way that we can use that index classifier really to distinguish different mechanisms here. And so we can identify which area indicate a compaction band like this one, compaction band, okay? And then which one is a compaction to shear enhanced compaction band or a compactive shear band here. And so different evolution will give us quite distinctive evolutions and for us really to identify the different mechanisms and to understand this phenomenon in a much clearer way than before here. Here, the further illustration of this microstructure changes related to different processes here. Okay. And further, and we extend this one to a saturated sandstone case in a similar way as I showed for the previous hydromechanical carving here. Okay, and essentially we use the same RVE and then but consider the pore pressure as a global variable to be solved. Still use the Tasaki, the effective stress principle for the RVE. And this is a comparison here. Okay, we consider three cases with the same RVE. One is dry, one is drained case, one is globally undrained here. Okay, and then both at the same, all at the same confining pressure here. So this is a comparison of the two, dry case and then a saturated undrained case. For the dry case, and then you form a clear cut of compaction band, and where this microstructure will compressed mostly, as you can see here. And then for this saturated sandstone and then globally undrained condition, and at the beginning you have initiation, but and quickly it develops a shear band. This is what we call a compactive shear band, and we can see it again. So for this point, it initiated from this position. At beginning slightly is compaction, but quickly going to this shear band pattern. And as you can see from this RVE, the shear deformation is quite evident and clear. And so this way that we can capture the subtle influence of this reduction in confinement pressure, how would that totally change this shear band patterns here, right? We can further look at how the comparison of this compaction and also shear distortion are developed in the two comparison cases. This is the further indication that if we further have another confining pressure and form a shear band at the beginning, and the shear band from the compression band at the beginning, the compression band formed when the compacted, the density, the porosity is reduced, and so the water within the pores will be squeezed out. You can see the density flux will flow out here. Okay. And later on, you can further develop a compactive shear band here, and then you can see here this compactive means that still there are some small amount of this density flux will squeeze the water and out of this shear band. So this is basically a deformation band transit from this compactive band to a shear band, right? And so this is the further comparison of the two cases. One of the same case, but one we use this debonding number. Basically, the bond between particles were lost. We count that. This is the compression, and then one later on will form a shear band along this one. This is the average particle rotation here. So the particle rotation is quite clear, evident during the shear band formation case, but not that so along this compression band case. Okay, and so the rotation is not evident for this compaction stage, but for the shear band case, it's quite evident. And then this is a further the density flux, and I showed, and pore pressure variations. So density flux when compression band occurs, and it's ready to squeeze the water out quite clearly, and this is the pore pressure change. And then later on, it really form the shear band along this direction. The shear band again, still the water will be squeezed out because it's densified within the shear band here. And then there's the further quantitative analysis. We can see that how during this unjoined shearing, the accessible pressure will affect their stress regimes, and then to change the band formation from a compression band to a shear band here, which I'm not going to discuss in detail here. This is another plot to indicate that how in this stress path changes, just because this develop accessible pressure will lower down the effective stress, and then to cause the band formation condition changes from compression band to a shear band. Yeah. Okay, so here we further use that indicator to differentiate the different band relations, and we can further use that to simulate a borehole failure problems, and which were in the petroleum engineering, and this is called a slot or fracture breakout. You can really to create some a borehole, and then at certain positions, and then really break out and form a fracture here. And this is our simulation. This is experimental observation. This is our simulation for the breakout, and it depends on a lot of features that we can reproduce. These are further variations if we really change the boundary condition in situ stress, and their formation can be totally different. Okay, and I think we probably up here we need to have a break, right?
So Jiran,
yeah.
So it is now 10:45. Shall we take a break, and then after your lunch we'll resume? What do you think?
Yeah, sure. Let's have a break, and I will continue after lunch, right? So we'll come back at
half past 11, IST. Is that okay?
Yeah,
45
sure.
minutes? Okay, so then we'll resume at 11:45. But before we close, can I open the floor for questions, if any?
Sure.
Okay.
Yeah.
So, yeah, 1 minute.
Yeah.
There seems to be a question here.
Professor Jidong, I have a question regarding the boundary conditions in triaxial testing. So you have performed both drained and undrained hydromechanical simulations.
Yeah.
So can you briefly give what kind of boundary conditions you have given for drained case so that no excess pore pressures got generated within the system?
For drained condition, for example, for this sample, right? For this example, and for drained condition, because the drain and we don't think the pore pressure matters because pore pressure will totally dissipate, and if there's any excess pore pressure will dissipate, right? And so in that case, we treat it as like a equivalent to dry condition. We don't consider pore pressure at all. But for undrained condition, it's different. Undrained condition is for these samples, and then the whole sample is saturated, whole saturated sample, and then all the four boundaries is undrained. We use a membrane to cut off the flux is there. But within the sample, within each elements, and it's a potential is freely drained condition. So the water can drain from one element to another element. So this is how we.
I understand for the undrained condition, but for the drained condition, as you mentioned, it's a hydromechanical modeling. I thought you might also be solving for pore pressures.
No, we didn't. We actually did simulate that one, but we found that it has no difference than the purely dry condition for the totally drained condition.
Yeah, because in the drained, if we solve for pore pressures, we have to make sure that no excess pore pressures get generated, which means
That's right.
The flow should be fast enough to get it drained.
That's right.
Under the loading. Yeah. So another question is regarding the mesh sensitivity. You have performed a lot of simulations with the constant mesh, I suppose, because all the quad elements I could see in all your simulations with almost an average size becoming constant. So can you comment on that, like how the mesh size affects the final outcome?
Yeah, that is a very good question. Indeed, in our simulation, we still resort to so-called first order finite element method, and where we don't consider we didn't introduce any gradient or other non-local features into it to resolve this mesh dependency. That's why then we have done mesh sensitivity study, and then to see that in our simulation this mesh can generate relatively consistent results. So mesh sensitivity still persists to this problem. We didn't resolve it. And that mesh sensitivity need to be resolved. Either you introduce like gradient terms, and for the multi-scale property, you can really introduce another kind of like we call a cost rate continuum model, and then put in the DEM simulations and use that really to partially to resolve it. Or in a continuum level, and some people use this smoothed particle FEM as a regulators to this mesh, and then for that purpose to mitigate this mesh dependence.
Yeah, thank you very much.
Thank you.
Are there any further questions? Oh, there seems to be one more question.
Good morning, Professor. Am I audible?
Good morning.
Yes. In one of the examples you showed, the retaining wall problem. Yeah, there was a smooth boundary condition also simulated.
Yeah.
Any particular relevance in looking at those results? Because I'm assuming there will be high friction between the soil and the wall.
Well, in reality and indeed, the experimentalists, they have done quite different setup. Smooth sample does exist, in a way that you can ready to put a lot of
not this slide. There was a retaining wall problem. I forgot the slide number.
Wall. Oh yeah, return wall is ideal as a situation here. Ideal as situation.
The next slide.
Yeah, we indeed wanted to look at the more realistic case with the rough boundary, right? And then idealized solution with a smooth boundary to look at the difference and how the difference two extreme. One is idealized, which is not realistic. There's a rough boundary, which is total hold samples, right? And we expect the real solutions will be in between, right? So the smooth boundary content indeed is just idealized situation.
All right. One more question: the cavity expansion problem. The next one.
This one.
What I'm unable to understand the relevance of this. Like we are looking at the distortion bands in the soil, and what is the inference that we take? What are we trying to prevent or study in this particular case?
So, so can you repeat your question again? So, what is your question about?
So, we are studying the deformation of the soil through this cavity expansion problem.
Yeah.
What is the relevance? What is the specific engineering question that we are trying to answer in this particular problem?
Oh, indeed, this one is there is still a petroleum engineering, and they look at the borehole instability. And then, for example, during the pressure rise stage, and then you want to maintain the borehole stable. But sometimes in a lot of in early days, petroleum exploration, and they find the borehole can collapse just because you develop a certain kind of like the shear band at a certain place. And this one called a borehole instability. So let's continue with the discussion of this multi-scale modeling by FEM and DM. But I wish really to emphasize on the coupling framework, and where that we coupled a continuum method like FEM, and with a particle scale micromechanics approach like DM. Indeed, we can take advantage of the benefits offered by both approaches. For example, we can incorporate any enrichment at the particle scale, at the RVE scale. This is what I'm going to show in the following, that how we can really to further incorporate any kind of advances in the micromechanics, in DM modeling, in particle modeling, and then to this multi-scale approach. For example, particle green shape, for example, and in the previous example, the mostly other than the first example, we use the peanut shape with 2D, and we can actually consider more realistic particle shape. And for example, we can use this so-called poly super ellipsoid. And so this is the approach developed by my colleague and a research assistant professor, Dr. Shiwei Zhao with me. And then we basically use this mathematical expression to express a super ellipsoidal expressions by choosing the different parameters for epsilon, and then we can really generate a different shape. And so, and we put a so-called poly, mean that for the natural sand, and their shape is kind of quite complicated. And so what we do is we basically cut off a certain super ellipsoid, and then to stitch them together, and then to form a whatever the shape that are required by a natural sand. And then we ensure that when we stitch them together, and they remain their the smoothness at this part here. So this is what we do here. For example, we can use a total of 6 or 7 or 8 different part of this different super ellipsoid shape, and then stick them together, and then we form a shape. The shape further will be validated by the real sand like that one. Of course, it's not 100% match, and then we can allow certain kind of like confidence, and then to reproduce a shape here. And with that, and we can generate a total laboratory of them, and use that lab to generate the RVE, the discrete element assembly for the representative volume element. Okay, this is what we do. We can develop further more advanced contact detection solutions by such approach and generate the RVE. And use that RVE for the RVE solving. For example, we can embed such RVE in that multi-scale approach, and then to generate a more realistic particle scale response for the different boundary value problem here. And then we can also use other methods. For example, we can use this Fourier shape described based method, or we use this spherical harmonics method and to generate different RVEs. Or we can use this level set method to reproduce this X-ray CT mapping realized particle and generate a packet to embed into this multi-scale approach here. So those are the enrichment we can easily, conveniently incorporate into this multi-scale coupling framework here. And more recently, in my group from postdoc Dr. Zhengxiu Lai, and use this called sun distance field method, and then to generate this is a more robust approach. And then we can really cover all the previous methods we mentioned as a special case to generate a realistic particle shape, including like a poly superlabosoid and poly super quadratics, and the spherical harmonics, polyhedron, level set, and the mixed shape. As you can see, here the polyhedron and this mixed shape, and it can be convex, concave and convex. And of course, with concave, and then the contact detection can be a challenge, but this level set help us, this SDF help really to resolve the contact detection as well. This can be incorporated into the DEM for the multi-scale modeling. And further, we have developed another, still use SDF to generate this more complex granular particle. This is a coral particle here, okay? And then this coral sand, and the coral sand is featured by this double porosity in a way that each individual coral sand, it have a internal pore. And then when you put such a assembly of the coral sand together, and they have this interparticle pore as well. So we have this another kind of like the dual porosity structure. And then this could be quite a challenge further if you want to couple with a fluid here. But again, that if you want to study the behavior of the coral sand as related to the boundary value problem, and we can incorporate this generation of this coral sand into DM, and then couple with the FEM to solve the problem here. And this is what I mentioned before. This is spherical harmonics, and this is again, this is the previous one, but I don't want to repeat again. X-ray, and then for shape describers, and also this spherical harmonics here. And then another feature is, as I mentioned on Monday, would be particle crushing. The green crushing, and then has been studied by a quite range of different approaches. One is called a clumped particle method. We can really clump sphere particle together, use certain bounded particle models, and then when crushing condition satisfy this debonding criterion, and then the particle can crush along certain surfaces. And so this is one method that are popular in the literature. Another method would be the so-called particle replacing method. You have a certain particle when the crushing criterion is met, and then you can replace this sphere particle into a number of small particles, and particle size and number can be specified in advance here. And then a third method is FDEM. It's mentioned basically similar to in video particle, or the FEM by FEM mesh, and then use FEM and assume certain constraint models for each FEM mesh, and then to solve it. And when the crossing criteria met, and then also the FEM itself generate a breaking part. And so this is the FDM method here. So what we do is, we recently use a paradynamics method coupled with other methods to study the crossing. Paradynamics is a new non-local continuum-based method to simulate each particle by like a bounded particle, but different. They basically interact with material point interact with the bound. The bound can be specified different models here. It's very efficient in solving this fraction, fragmentation, or cracking problems here. This is a simulation of a single particle crossing can be by this paradigm here, and we compare it to the experimental observation here. And then essentially we want to incorporate this paradigm and then into this particle crossing simulation in a way that this paradigm can generate a more realistic crossing patterns in terms of the particle size and particle shape. And then we can further incorporate the crossed child particle shape and size into further the next step crossing simulation here. So what we do is for a single particle, when the crossing criterion is met, we use paradigm to simulate it and find the crossed child particle, and then we further use a so-called CGAL, computational geometry library, and then to describe the surface, and then to put the surface into another numerical method we call non-smooth contact dynamics. And this non-smooth contact dynamics is a rigid body representation, a counterpart of the DM. DM basically is a soft particle method. You allow particle overlap to generate contact force. But this is a rigid body contact dynamics things, and then this will be more efficient really to do this contact detection and to handle the non-smooth, non-spherical particle shapes here. We couple this NSCD with paradigm. So in a way that this serves as the DM packing, and then subject to all kind of external load. And then each loading step, and we check through the particles, and then we find certain crossing criteria is met, and then we put that specific, like this particle, on the by DM, treated by DM, at the in situ contact condition. If they have 4 or 5 contact points, and we substitute this same particle at the same contact condition, same contact force. And then we use paradynamics to simulate it, to get the breakage. Once breakage, and the individual child particle will put back into the locations. That is reach the equilibrium and go on to the next loading step. And then so what we do is that we use either Project Chrono engine or the bullet physics engine, and to serve the non-smooth contact dynamics solver, and we use the Sandia National Labs paradigm to serve this PD solver here. We use this CGAL library and to connect them together, and to in the whole process we respect the realistic particle shapes and size during this crossing process here. So this is the one thing that we generated for such a packing, and we use NCSD to simulate a 1D compression. Lateral deformation is a constraint. We apply a compression from the top and bottom, and the particle will experience such a continuous crossing, and wherever its shape, the child particle shape, or will be retained until before the next crossing step, and then so the whole process can be continually crossed and along until to the certain criterion here. Okay, for example, this is the crossing process at the beginning, and cross to the B point, and then further cross to C and D here. And so the total number of other child particle can be crossed from the beginning of like 600 particles, more or less the same uniform, slightly Granular distribution used, and then to a total number around like 26,000 particles. You can continue to cross it, but with the further continual crossing, the particle becomes smaller. And we know that during in both DM and NSCD, and then the computing time step will depend on smaller particle. In that sense, and then with the smaller particle, the more particle number, the smaller particle size, and the computational efficiency will be very, very high. That is make this particle crossing simulation so challenging really to handle. Yeah. But essentially, this will open up the avenue that we can really to incorporate a very good particle crossing engine, and considering realistic particle size and shape evolutions into a multi-scale simulation platform, and where we can really to consider simulate a boundary value problems that involve particle crossing. And this is the further example that we do a true triaxial compression to look at the particle size evolutions, and then to look at the shapes like a sphericity, and also look at the coordination changes, look at their strengths, and look at also the breakage index, and then for example defined by Harding for that purpose, and do all kind of different analysis here. And so this is what I wish really to show for this part, that we generate a general concept of a coupling that we can couple a continuum approach like FEM, and with a particle scale simulation to like DM to really tackle engineering challenges here. And this FEM+DEM coupling enable us really to integrate the particle scale physics and with a engineering scale loading, and to provide a solution which can help us to bypass this phenomenological assumption here. Okay, and this gives us a unified way to treat to unify the continuum of mechanics with micromechanics, and then for future study of granular mechanics. And then before I go on to the MPM part, do you have any question for this part? I can answer a couple of questions before I move on.